Hello, Titans. In my last video, I described the relationship between specific heat and heat. Heat is the amount of energy contained in something. Specific heat is a property of that something that describes how much heat it can contain. For example, water has got a very high specific heat. It takes a lot of energy to warm up water. What I want to do now is build on that concept by describing, actually, you know what? I'm going to use the same demo I just did. We're going to talk about this demo. I added 500 grams of 100 degrees Celsius steel to 500 grams of water. Now, that makes a lame problem when they're the same. So I'm going to tweak it just a little bit. Let's do a problem where we have 1,000 grams of, I'm going to call it iron. Fe is iron, right? 1,000 grams of iron at 100 degrees Celsius. And let's drop it into a beaker that contains, let's say, 750 grams of H2O at, let's say, room temperature, we'll call it 21 degrees Celsius. My question is, what's going to happen to those two materials when we mix them? What will be the final temperature? Well, what are we going to do? First of all, we're going to make an assumption that we are in an insulated container. That may seem a bit of a stretch, but if we do this experiment inside a thermos, we can assume that we're not losing a lot of heat. In physics, we use a device called a calorimeter, which is basically a double-walled container that makes a pretty good insulator, and we can do this experiment inside that calorimeter. So I think it's safe to say that we don't necessarily have to lose a lot of heat in this experiment. If that's true, then we're going to use that concept and say heat loss equals heat gain. That's the law of conservation of energy, isn't it? One loses heat, the other gains heat. I'm going to suggest that we draw a thermometer to help us keep track of all this stuff. So down low on my thermometer is 21 degrees Celsius. That is H2O. That is 750 grams. High up on my thermometer is 100 degrees Celsius, and that is iron, and that is 1,000 grams. So I've taken my story problem, which I had written sort of as a picture, and I've turned it into values on a thermometer. Where are we going to end up? Well, somewhere in the middle, right? I'll call it T. So what do we know about the heat lost by the iron compared to the heat gained by the water? Well, they better be the same, right? Energy is conserved in any situation. Heat's not going anywhere else. It's got to be in one of those two places. Now, the heat lost by the iron will be a negative value because we're losing it. The heat gained by the water would be positive because we're gaining it. So but I'm setting it like they're equal. So I'm going to have to allow for that. So we'll come back to that one. So let's set this up. How do I calculate heat loss? Well, heat, we said in our last video, is MC delta T. How do I calculate heat gain? Well, that's MC delta T. Now, that doesn't look like much of an equation, so we're going to need some subscripts here. What's losing heat? That's the iron. So I'm going to say iron mass, iron specific heat, and iron's delta T. And for water, I'll use W instead of H2O. It's easier to write W for water. So I've got a good equation. These are equal to each other. The heat lost by one is equal to the heat gained by the other. I know the mass of the water. That's 1,000 grams. I know C for, sorry, I said water, I meant iron. That's 1,000 grams. I know C for iron. I can look that up. I've got it on my table over here on the board. Delta T. Well, how much is the iron losing in terms of temperature? Well, it's going from 100 down to T, right? Can I say 100 minus T? Is that fair? I think so. So I'm going to say M iron, C iron, and then instead of delta T, I'm going to write 100 degrees Celsius minus T. How about over here? Mass of the water, I know. C for water, I can look up. Temperature for the water, well, it's going from 21 up to T, but I said I wanted them both to be positive, right? So I'm going to go the same way. I'm going to go down. I'm going to say T minus 21. That's going to make both of these values positive, and I'll get a true equality here. So I'm going to say T minus 21. And now I got a good equation. I know every number except for T. I should be able to make this work. So I'm going to plug in some numbers here. Mass of the iron, 1,000 grams. C for iron. That is, I'm looking on my board, I have 448. That is joules per kilogram per degree Celsius times 100 minus T, 100 degrees Celsius minus T, equals mass of the water, that was 750 grams, times C for water, that is 4,186, 4186 joules per kilogram per Celsius degree. And the delta T for the water, we said was T minus 21 degrees Celsius, T minus 21 degrees Celsius. I got it to fit on the board. That's a big, ugly equation, isn't it? Let's clean it up a little bit. First of all, I see grams here and kilograms here. That's a problem, isn't it? Well, not necessarily, because I have grams on both sides. Can I just cancel those out? I think I can. For that matter, I have joules per calorie per Celsius degree on both sides. Wipe those out. And suddenly this problem looks a lot easier. So 1,000 times 448 times 100. That's 448,000,000. 44,800,000, if I did that math right in my head, degrees Celsius, minus 1,000 times 448 T. Equals. Oh, I am not going to be able to do this in my head. I want 750 times 4186. $750 times 4186. That is 3,139,500. T minus that times 21. So times 21. I have 665,929,500 degrees Celsius. I almost fit on the screen. There we are. That is awful. But you'll notice I have two numbers in degrees Celsius, two numbers in in T's. I should be able to combine my like terms. If I add 448,000 to this one, and I add this number back to this side, so I'm going to do that one first because I have it on my calculator. So plus 44,800,000. I see 110,729,500 degrees Celsius equals this number minus 448,000. So 313,9500. I subtracted instead of adding, didn't I? 65 million. Nope, I added. Okay. So I want to add these two numbers. So 313,9500 plus 448,000. This is good video, isn't it? 358,7500 T. And now can we find our temperature? Piece of cake. Divide both sides by this number. I get 30.8. 86, 87 actually, degrees Celsius. So we started at 21 for the water. We started at 100 for the iron. 38 is way closer to water than it is to iron. Did I screw this up? Or excuse me, 31 degrees is way closer to 21. So this only went up 10 degrees. This one cooled from 100 all the way down to 31. It cooled down by almost 70 degrees. That doesn't feel right. Did I screw something up? Hopefully, if you think of what we saw in the last video, you recognize, no, I didn't screw this up. Water's got a way higher specific heat, meaning it doesn't warm up as much. It contains a whole lot of heat by itself. It doesn't want to change much. Iron has a very low specific heat. It doesn't mind changing its temperature, and it changes fast. So my calculation is good. What if I had a brass stirring rod in my container to stir it up. And the brass rod started out at 21 degrees Celsius. Well, I could have said water and brass at 21 degrees Celsius, and I could have said, what's gaining heat? Water plus MC delta T for brass. I would have had just one more set of information, but I could totally do it. That's not an uncommon kind of problem because in what we call a calorimeter that I mentioned earlier, it's not uncommon to have a little stirring rod in there, and it's technically part of our experiment, so we should include it. But we can have multiple things going on. If we had this is a glass container that I was using. Glass is quite insulated. It tends not to warm up much. But if we had used a steel pan, well, the steel pan might have become part of our problem, gaining heat. So we've got to consider things like that. But I hope that helps you understand how we can do, these are called calorimetry problems, when we mix two different samples together, how we can find their final temperature. Hopefully that works for you. Hope you have a wonderful day, Titans.